All right, welcome back, everyone, for the part two of the lecture on clouds and precipitation. We're going to continue on talking about rain. So rain is just liquid precipitation. You've all probably experienced it before. And so when we talk about rain, it's always important to think about the individual droplets and how they form. And so rain droplets are always in a constant battle between how much water they're absorbing from the water vapor in the air, as well as the evaporation that's occurring and losing water. And so that evaporation is greater with the greater curvature of the surface. And so small water droplets will have a higher evaporation rate. And so if a water droplet is too small, then it can evaporate completely away and it won't survive. Whereas a large water droplet will have a lower evaporation rate and therefore can continue to build and get larger. You might be asking then, how does rain actually form in the first place? And that's through something called condensation nuclei. Pretty much all rain starts on a grain of dust, a little particle, or another larger water droplet. And so you need some surface in order to start that condensation process. And so as you have these individual water molecules attaching to the surface of this dust, the adhesion allows it to combat that evaporation rate, and it can build up. And so you can see here that the evaporation rate is not as high when you have that condensation nuclei. These condensation nuclei tend to be extremely small, around 2 microns in diameter, but once they start having water droplets adhere to them, then they can form into much larger droplets. The droplets of water vapor in a cloud would be about 20 to 50 microns across, and then a raindrop is significantly larger, about 2 millimeters across, and that's when it starts to fall. So the rate at which a raindrop falls depends on the size of the raindrop. So the larger the raindrop, the faster it falls, and it falls until it reaches its terminal velocity. And it'll only fall if that terminal velocity is greater than the uplift rate caused by the wind in that cloud. So oftentimes you'll remember, to form a cloud in the first place, you have to have upward movement of wind and water vapor. And so therefore, in order for rain to occur, the falling velocity has to be able to be greater than that uplift rate. But also, raindrops have a mechanism to make sure that they don't get too big. And so as that raindrop falls, it collides with other water droplets and raindrops, and it grows larger and larger. But as it gets too large, it will break apart. So that growing phase is called collision and cohesion, as it collides with different water particles and grows larger and larger until it eventually breaks apart because of all the air that's now hitting it. All right, so you can see here that water is not evenly distributed, and rainfall not evenly distributed throughout the planet. So you can see that there's a very high concentration of precipitation near the equator, and that's related to that ITCZ that we talked about, where you have the convergence and low pressure system around the Hadley cells. Also, you have a lot of precipitation around the Amazon rainforest, and also different areas of the planet. So next, let's talk about rainbows. Always a fun topic and relevant to rain and precipitation. And so rainbows are formed when sunlight is reflected off of the inside of a collection of raindrops. And so as sunlight comes in, it enters the raindrop, it refracts or it splits up into its individual colors, just like a prism would, and then it reflects off the back of the raindrop in a process called total internal reflection, and then it bends and hits your eye. And so the red area of the rainbow is where that red light is at the right angle to hit your eye, whereas the blue and purple is where that sunlight is coming in at the right angle to hit your eye for that bend in the light. And so that refraction process is really important for the formation of the rainbow. So the blue light tends to bend more than the red light. And so you can see here that this red beam here, as the white light gets separated, doesn't bend as much as it enters into the raindrop. And that's what's causing the dispersion of the different colors of the light. And so double rainbows are also really cool. Hopefully you get to see one. And they kind of show this process even more. So a normal rainbow will always have its blue and purple at the bottom and the red light at the top. And it'll always form a perfect 40 to 42 degree angle with the sun. So if the sun is here, this angle in here is the angle in which the light is being reflected back. And that's because of the angle at which the light is refracted within the raindrop. And because the red light gets bent less, that light tends to be on top. So at the 42 degree angle. But for a double rainbow, you have double internal reflection. And so instead of the light hitting the back of the raindrop once and refracting out, it's bouncing inside the raindrop twice. So once here and again here before it eventually comes out of the raindrop and comes out. And as a result of that double bouncing, the rainbow is flipped. And so the purple is on, or blue is on top, and the red is on the bottom. And because some of that light is lost and not all of it is perfectly reflected, the double rainbow tends to be a lot less bright than the single normal rainbow. And because it's refracting at different angles, it is always higher than the single rainbow, and it forms a 52 degree angle with the sun. That's pretty cool. Yeah. So next, let's talk about snow. So snow is just crystallized frozen precipitation. You can see here a beautiful picture of a snow crystal here. This was a picture taken by Wilson Bentley, who was the first ever to take magnified photos of snowflakes and figured out a way to make sure that they stayed frozen while he put them underneath his microscope. And he has a whole collection of these beautiful snowflakes. So snowflakes have a process called the Bergeron process. Because the evaporation or the sublimation rate from a snowflake is less than the evaporation from a water droplet, the Bergeron process says that snowflakes can actually steal water vapor from that water droplet. And so as it evaporates off, more water will crystallize onto this supersaturated ice crystal, and the ice crystal will grow. And that's how a lot of ice crystals grow in clouds, by stealing their water from water droplets. There's a number of different shapes that an ice crystal can be in, not just that pretty dendrite, that's what it's called, that we just saw, which has the 6 sides to it. But you can also have needles, plates, all sorts of different shapes, columns, and the shape of the snow crystal depends on the temperature at which it forms, as well as the saturation of the water vapor. And so the higher the concentration of the water vapor, for example, the more likely that you're going to have these dendrites forming. Whereas with less water vapor, and especially with higher temperatures, you tend to not form as pretty crystals, and they tend to be just these prism shapes. But after it reaches the ground, and sometimes even before it, the snow starts to metamorphose. That's the process that we call when crystals start to break down and form into kind of conglomerated clusters. And so you have repeated cycles of melting and freezing, and that will kind of weld these snow crystals together, and they start to get rounded and don't have their spiky dendritic arms anymore, and instead are more of these clumpy large crystals. You can see here the distribution of snow throughout the globe. Antarctica and Greenland, of course, having areas of 100% snowfall or snow cover, whereas the majority of the snow occurring on Earth is in the northern hemisphere, with snow in Siberia and Canada mostly. We also have snow a lot in the Andes and Himalayas and the Rockies as well. That snow cover has been on a steady trajectory because of climate change. And so the trend in snow extent is different depending on the season. And that's because climate change does not only increase the temperature and therefore melts more snow and makes more snow fall as rain instead, but it also brings more precipitation. As you have more evaporation occurring due to climate change, you have, especially in cold areas, you have more snowfall occurring. So you have more snowfall and more melting. So sometimes, in some seasons, that counteracts each other. In general, this is data from the Rutgers Climate Institute, you have an increase in snow cover in the fall, at least in the northern hemisphere. You have kind of a stagnant snow cover in the winter, and you have a very dramatic decrease of snow cover in the spring as the winter season gets shorter and shorter, and melt occurs earlier and earlier due to climate change. And so these combined effects mean that snow cover has been decreasing on an annual basis due to climate change. So next, we're going to talk about hail, and I think a good way to learn about hail is through this video, and so we'll watch that now.
Hailstones crash through windows. They shred trees and crops, pummel livestock, damage roofs, wreak havoc on cars and everything underneath its wrath. Hail can turn a scorching summer ground into a winter wonderland in minutes. Oh my God. Sometimes baseballs just fall from the sky. Other times, strong winds hurl hailstones sideways like bullets. If you're caught away from shelter during a severe hailstorm, you've got a problem. you're a storm chaser, hail is your nemesis.
Oh man, no hail, please.
Yet you proudly wear your hail dents like victory battle scars.
Brand new truck, right?
Oh yeah.
A hailstone forms as a tiny water droplet journeys up above the freezing level in some of the most beautiful and dramatic thunderstorms. But how does it get so big? And how big can it get?
Look at that. They're everywhere.
In an environment conducive of a severe hailstorm, this rising air or updraft is often exploding into lowered freezing levels. This is the factory where hail is made. When the droplet freezes, this process releases heat, which keeps the stone's exterior in a sticky liquid phase. As the little stone journeys through the cloud, it captures more and more water on the surface. The inner layer freezes, and the hailstone grows a layer. You can see the different onion-like layers in many of the stones. Hailstones can also grow by colliding and conglomerating with others, one of the reasons they come in such a myriad of funky shapes. Here's a disc-shaped stone with crystal star-like protrusions. Here's one shaped like a bomb. Here's one shaped like Stewie Griffin. These upward winds sustain ice pebbles, and the longer they hang around up there, the larger they tend to get. But some intense updrafts blow up over 100 miles per hour. This is where things really start to get freaky.
All right, cool. So just to recap, that hail always forms due to updrafts within thunderstorms. And as you get stronger and stronger updrafts that are causing that hailstone to lift up and move through more moist air, then it can get larger and larger and collide with more other hailstones until it eventually falls. So let's next talk about sleet, freezing rain, and graupel. So these different phenomena occur when snowfall hits a warm patch of air, and that air is warm enough to melt that snow as it falls. And so sleet is snow that has partially melted and refrozen while falling. And you can see that here, that you have a cloud that's snowing out, it hits this warm layer and partially melts, and then it hits a cold layer again and refreezes. And it tends to form these kind of small balls of ice as well. Freezing rain can be really awful if you're ever in it, and it just occurs when that warm layer is a little bit thicker, and so you don't have that melted snowflake refreezing completely. That cold layer isn't thick enough, and so when it hits the ground, it falls as rain that's at 0 degrees Celsius. And so usually as soon as it hits a cold surface, then it can freeze. And it's just really unpleasant to be in if you have the rain that's just about to freeze right on you. And then graupel is these kind of little ice balls that can form, is snowflakes that collect super cooled water droplets on its surface. And so this is snow that's gone through a layer of supersaturated water that didn't have a condensation nuclei. And so instead it's using that snowflake as a condensation nuclei. And so they're kind of just like snow, but they're not that pretty snowflake shape because they've had glommed onto it more water. So unlike hail, hail usually forms during warm conditions, at the surface at least. So hail, you have water vapor rising up high up into the atmosphere in that thundercloud, and it's freezing because it's so high up, and then it falls and doesn't melt before it reaches the ground. Whereas sleet and freezing rain and graupel all start off in cold conditions, and it's starting as snow and then hits a warmer layer. And so generally sleet, freezing rain, and graupel occur when it's colder out compared to when it's hailing. Some other cool frost-related features are hoarfrost and rime. So rime is ice that gets frozen onto a surface because of supercooled water vapor in the air. So rime forms as you have freezing fog. So fog that's saturated with supercooled water, but doesn't have a place to actually form those ice crystals. And so as it touches something, such as a plant here, you'll have that deposition of ice crystals onto that surface. And that's always going to be on the windward side of that surface where the wind is blowing onto. And so you can see that here as well. This is a picture that I took in Greenland. This is a rope that we hang between our tents just in case we ever have a really bad snowy day and we can't see between our tents, and we use the rope. And the ice crystals have completely formed all over this rope, which is pretty cool. So unlike rime, though, hoarfrost occurs just due to high humidity and generally clear sky conditions. And so rime usually will be on just one side of an object and kind of look like it's been windswept, whereas hoarfrost can kind of surround an entire object like you see this rope here. But they're fairly similar processes of supercooled water hitting something and freezing. Another really cool feature are frost flowers. If you ever get to see these, they're very, very beautiful. You'll see them all over the Catskills, especially in the winter months. So frost flowers are formed when groundwater seeps slowly out of a log or some soil or a plant. And because of that, the structure of the log itself, with those kind of tubes inside of it, you have ice crystals slowly forming out of it. And it forms these wispy, extremely delicate formations that you see here, which are very cool features. But the important thing to know is that they're forming out of the system instead of being deposited from the atmosphere. And the last thing that we're going to talk about is cloud seeding. So cloud seeding is a very cool man-made process in which you can have a plane or a weather balloon or some other object depositing condensation nuclei into a cloud in order to try to induce precipitation. So oftentimes that condensation nuclei is silver iodine or dry ice that's shot out of a plane in order to cause that water vapor to condense and rain out so you can have sunny weather afterwards. And so it's really helpful if you want to reduce the size of hailstones because they'll fall out more easily or clear an area of fog, though it's a fairly expensive process. And it usually has fairly minimal environmental impacts, but it's fairly recent invention. So we don't fully know if there's any toxicity that can really occur from it. We saw too that China was using cloud seeding in order to clear clouds for the Olympics a few years ago, and most recently for a military parade. So it's used all over the world in order to have a kind of an anthropogenic effect on cloud cover in an area. All right, so that just about covers everything. In summary, we talked about condensation and different vocabulary around that. We talked about the different cloud types and the 3 different cloud layers. We talked about fog, and we talked about rain and the global distribution of precipitation. We talked about how rainbows formed, snow and different snow crystal formation, hail formation, sleet, freezing rain, and graupel, and then lastly, cloud seeding. So that just about covers everything for clouds and precipitation. And I will see you guys in the next lecture. All right, thank you.